Hello and welcome to the second lecture of Rigidity of Magic Square game. This is the ninth lecture in the series of lectures on quantum entanglement and non-local games. So here we'll continue with the proof to show that there is a unique solution in order to win the Magic Square game with probability 1. So in the last lecture we already saw some necessary conditions which any optimal solution, any solution which wins the Magic Square game with probability 1, it must satisfy. So what were these conditions? So firstly we had condition 0, which is like kind of an assumption. So here we assume that Alice and Bob share a full Schmidt rank state. Then after this we had a couple of we had 4 conditions. So firstly, that Alice's observable was supposed to be independent of the constraint index. Bob's observable is the transpose of Alice's observable, and Alice's observables in the same constraint, they multiply to either plus identity or minus identity depending on the constraint. And finally, observables in the same row and column, they must commute with each other. So we saw that any optimal strategy which wins the Magic Square game with probability 1 must satisfy these 4 conditions. This is of course assuming condition 0, which says that the shared entangled state is full Schmidt rank. Okay, so now we'll use these 4 conditions in order to show that up to unitary transformations, up to local unitaries and some ancillar qubits, our solution is exactly the same as the optimal strategy which we had earlier seen. So let's continue with that. Okay. So firstly our claim, so we have already seen that the operators in the same row and column, they commute with each other. Now we are making a stronger claim, which is that observables not in same column or row, they anti-commute with each other. And actually we'll only need this condition for A2 and A4. So let's draw the grid of observables which we have. So Alice has an observable for each variable which it can take as input. So Alice takes a constraint as input and then it measures all the variables in the corresponding row and column for the given constraint. Okay. Okay. So our claim is that observables which are not in the same row or column, they must anti-commute. Okay. So we will now try to prove this. Okay. In order to prove this, we will actually take a specific pair of observables, and the proof is actually similar for every pair of observables which neither lie in the same row nor lie in the same column. So we take an example, A2 and A4. Okay, so what we are going to show is that A2, A4 is minus of A4, A2. So how do we show that? Okay, and the same idea will carry for, you can take like any other observables like A4, A8 or even like A2, A7, A1, A8, A3, A5. So any pair you can take. We'll actually work with A2, A4 and the rest of the proof will also require us to use A2 and A4 only. Okay, so I'll leave as homework for the proof of any other pair of observables. Okay. So let's see. So how do we show this thing? So from the 4 necessary conditions, what we have is that A1, A2, A3. So since they lie in row 1 and the binary variables for row 1 must sum to 0 mod 2, so we must have A1, A2, A3 to be identity. Okay. And now if I multiply by A3, so what I'll get is that A1, A2, A3. So I am post multiplying both sides of equation by A3. So this is A3 and A3 square is also identity. So what I'm going to get is that A1, A2 is 3. right. Now similarly from the second row, what I can get is that A4, A5 is A6. So, okay, so I can have this condition in the second row also. Now let me look at the first column. So from first column what I have is that A7 is A1, A4. Okay, again like the first column, so observables multiply to identity and then I post multiply both sides by A7 and I am going to get A7 is A1, A4. And now if I look at the second column, I am going to get A8 is A2, A5. A2, A5. Okay, and so this is equation 3, this is equation 4. Okay, so now what we are going to do is that we take row 3 and we take column 3. So from row 3 what I have is that plus I equals, okay, so this is row 3, A7, A8, A9. So these also they sum to 0 mod 2, right? So their product should be identity. A7, A8, A9. And here I substitute the values of A7 and A8 from equations 3 and 4. So I'm going to get A1, A4, A2, A5 times A9. And from column 3, what I get is that A3, A6, A9 must be minus I. So A3 and A6 are what are obtained from equations 1 and 2. Okay, so I got A3 as A1, A2, A6 as A4, A5. A1, A2, A4, A5. This equals minus I. So let's compare these two now. So I have plus I equals A1, A4, A2, A5, A9. And this is negative of A1, A2, A4, A5, A9, right? Because these product to minus I. A1, A2, A4, A5 and A9. So now A1 and A9 and A5, so all these are invertible operators, so which means that I can multiply by their inverses and this will enable me to cancel out the elements. So cancelling the elements, so I can cancel out A9, I can cancel out A1, I can cancel out A5. Okay, so this no longer remains identity now because I've cancelled out the elements. But what I'm now going to get is that A4, A2 is minus of A2, A4. So A2 and A4 anti-commute. And as a homework, prove this for other pairs. Of variables which are not in same row or column. Okay, but actually we'll need only for A2 and A4, so that's why I only prove for this, but anyways the proof is similar. So let's continue. Now we have already shown that A2 and A4 anti-commute, and in lecture 7 we had seen a lemma that if you have anti-commuting pairs of observables, then since A2, A4 anti-commute, so there exists a unitary U such that up to this unitary transformation, A2 is going to be Z tensor IM and A4 is going to be X tensor IM. Okay, so this is assuming that A2 and A4 are 2m dimensional matrices, right? So they have to be even dimensional. That's also we saw for them to anti-commute. So A2 and A4 have to be even dimensional, and if they are 2m dimensional, then A2 up to unitary transformation is Z tensor IM and A4 is X tensor IM. Now we see that, so let's look at A5. Now A5 and A2 are in the same column, so they commute with each other, and A5 and A4 are also in the same column, so they commute with each other. Okay, and similarly A1 also commutes with both A2 and A4. So A5 commutes with both A2 and A4, and A1 also commutes with both A2 and A4. And this enables us to deduce another property. So we will actually show this via a lemma. So that if A in C2m cross 2m commutes with both Z tensor IM and X tensor IM, then, or rather let me put it as if and only if. So A in C2m cross 2m commutes with both Z tensor IM and X tensor IM if and only if A equals I tensor B for some B in C m cross m. This is what we will try to prove. So let's prove this. So let A be equal to A11, A12, A21 and A22, where Aij's are m cross m matrices. Then A times Z tensor IM. Okay, let's try to compute this thing. So how would Z tensor IM look like? So this would look like minus plus IM, minus IM, and 0 is 0. Okay, so I have broken it as 4 m cross m matrices, and now when I am going to multiply this thing, these are also m cross m, so I can like perform block multiplication, and then I am going to get A11, A21 minus A12 minus A22, right? Because this, when the second sort of 0 minus I will multiply, there will be a minus I on this column. So this is what I get when I compute AZ tensor IM. Similarly, from block multiplication, you can also compute Z tensor IM times A, and that will give you A11, A12 minus A21 minus A22. Okay, and now if I compare these two, what I am going to get is that A21 is minus A21 and minus A12 is A12. So that would mean that A21 equals to minus A21, which means that this is 0. Similarly, A12 equals to minus A12 equals to 0. So therefore, A is a diagonal sort of it's block diagonal matrix. So here I have used the fact that it commutes with Z tensor IM. Now similarly, I can use the property that X tensor IM also commutes with this. That will give me at A11. Okay, so when I pre-multiply X tensor IM, so this you have to check. Okay, so check that this multiplication turns out to be A11, A22. Again, we will have to use block multiplication. If I post multiply, I am going to get 0, A22, A11 and 0. So here I am going to get that A11 must be equal to A22. So therefore A is now A11, A11, 0, 0. So it is block diagonal and the two blocks on the diagonal are also equal. So therefore this is of the form I tensor A11, which I can write it as I tensor B for B equals A11. So now what we saw was that, so A2 we have seen that it's of the form, so we have seen that A2 and A4 anti-commute. Once we saw that they were anti-commuting variables, I can take them to be Z tensor IM and X tensor IM. And both now A1 and A5, they commute with Z tensor IM and X tensor IM, so they have to be of the form I tensor B. So let's just summarize what we have until now. So we have that this is now Z tensor I, this is X tensor I, okay, this is I tensor B, this is I tensor C. So B and C are what I am taking to be from the previous lemma. So in the previous lemma I am showing that if any observable commutes with both Z tensor IM and X tensor IM, then it has to be of the form I tensor B. Okay, and so here for this one I am writing as I tensor B. For this one I need to choose a different variable, so I am calling it C. Okay, and now yeah, so actually we will need the fact that A1 and A5 also anti-commute, but the proof is also similar. So A1 and A5 also anti-commute because they neither lie in the same row nor in the same column. And from this what we are going to get is that B and C anti-commute. If B and C anti-commute with each other, that means that they also have to be of the form Z tensor identity and C is of the form X tensor identity. Therefore, there exists unitary up to which B equals Z tensor, and since B and C are both m dimensional, they have to be Z tensor identity on m by 2 and C has to be X tensor identity on m by 2. Okay, so what do we get? So we now include these also. Now again let's draw the grid. So A1 is I tensor B, B is Z tensor IM by 2. So this is I tensor Z tensor IM by 2. And A5 is I tensor C, C is X tensor IM by 2. So overall this is I tensor X tensor IM by 2. And then A2 and A4 are Z tensor I and X tensor I. So I am going to write it as Z tensor I tensor IM by 2. So overall it's IM, but IM can be written as I2 tensor IM by 2. These are all I2, X2, Z2, and this one is X2 tensor I2 tensor IM by 2. Okay, so this was X tensor I, but I am breaking I as I2 tensor IM by 2. Now I know that A3 is A1, A2, so I can just compute. So A3 has to be Z2 tensor IM by 2. Similarly, now this A6 has to be A4, A5, that this will be X2 tensor IM by 2. And now A7 has to be A1, A4. A1 times A4. So this has to be X2 tensor Z2 tensor IM by 2. And A8 has to be A2, A5. So this will be Z2 tensor X2 tensor IM by 2, and A9 will be A3 A6, so this will be ZX tensor IM by 2, but I can also write it as Y2 tensor IM by 2. Yeah, so ZX tensor ZX can also be written as so if I write it as iota XZ tensor iota XZ, that will have a minus sign. Yeah, so you work it out, it should turn out to be this thing. So yeah, so actually this has to be minus of ZX tensor minus ZX. So see, A9 is going to be minus ZX tensor ZX. Wait. Yeah, this has to be minus A7 A8, which equals to minus ZX tensor IM by 2, and I can write it as minus XZ tensor IM by 2, and this minus sign I can write it as iota square, and one iota will go with this XZ, the other iota will go with this. So overall this will be Y tensor IM by 2. Okay, so this proves what we want, and now since we want that the answers must be consistent with each other, so you see that this matrix of observables is exactly what we had in our strategy, but just that we haven't yet shown the form of the entangled state ket psi. But since the answers of Alice and Bob must be consistent, therefore we must have that psi Z2 tensor I2 tensor IM by 2 on Alice tensored with Z2 tensor I2 tensor IM by 2 on Bob on psi. This must be 1. Okay, and this is a unitary operator, so Z tensor I tensor Z tensor I, this entire product is unitary, and psi is a unit vector. So overall when I multiply it by ket psi, I am going to get a unit vector. Now I have two unit vectors whose dot product is 1, right? And by Cauchy-Schwarz inequality, the dot product has to be less than equal to 1 in magnitude, but since it is equal to 1, that means that they are parallel to each other, right? Because that's the only case wherein equality comes up in Cauchy-Schwarz inequality. And also the coefficient must be 1, right? Because their dot product is exactly 1. So they are parallel, and one is a ratio of the other, but that ratio also has to be 1 now. So therefore what we have is that this second quantity has to be 1. So Z2 tensor I2 tensor IM by 2 on Alice tensored Z2 tensor I2 tensored IM by 2 for Bob acting on ket psi must be equal to ket psi. So this means that ket psi is invariant under Z tensor I tensor Z tensor I, right? So it's invariant under Z acting on the first two qubits, on basically the first qubit of Alice and the first qubit of Bob. So therefore the first qubit of Alice and Bob is invariant under Z Alice Z Bob, and similarly again from consistency, right? So here for this consistency check, what we used was the A2 cell, but I could have also used the A4 cell. So answers to A4 must also be consistent, and then it will give me that psi is invariant under X Alice X Bob. Okay, first qubit is also invariant under X Alice X Bob, and the only state which is invariant under which is stabilized by ZA, ZB and XA, XB has to be equal to the APR state, which is 1 by root 2 0 0 AB plus 1 by root 2 1 1 AB. Okay, and similarly, so here I took A2 and A4, but if I now take say A1 and A5 and use the consistency conditions, I am going to get that second qubit is also of this form. Okay, so second qubit is also of the above form. So the overall state psi AB has to be 1 by root 2 0 0 A1 B1 plus 1 by root 2 0 0 1 1 A1 B1 tensored with 1 by root 2 0 0 A2 B2 plus 1 by root 2 1 1 A2 B2 tensored with ket phi ancilla. And this ancilla is not important because all the operators act on first and second qubits only. So what we have shown that up to these additional auxiliary or ancilla qubits, which we never measure, the strategy is of the form of what we discussed earlier as our optimal strategy. Right, of course we are assuming a local unitary transformation, which is also allowed. Yeah, so this finishes the proof of the rigidity of magic square game. Right, so we have seen the rigidity of CHSH game as well as that of magic square game. And some of the ideas for the optimal strategy can also be used to generalize to binary constraint system games. So binary constraint system games are those wherein, so here we saw that we had some constraints and we had some binary observables, and over there so these constraints here were arranged in the form of a magic square grid. But in general, in a binary constraint system game, we can have any sort of constraints, and Alice is given one of the constraints, Bob is given one of the variables in the given constraint. So these constraints are on the sum of binary observables, a few set of binary observables which either sum to 0 or 1 modulo 2. So I give one of the constraints to Alice and I give one of the variables in the constraint to Bob, and they have to output a satisfying assignment, and so they win if they are able to match their outputs, right? So if there is a so if all these constraints are like kind of disjoint, so there is no common variable in any of the constraints, then you can of course win with probability 1. But if there are intersecting variables and it turns out that the constraints are inconsistent, as we saw with magic square game, then it might not be possible to get a probability 1 solution classically. In quantumness, we can win provided we can obtain an operator solution, right? So this is how we generalize to binary constraint system games. You can read up some of it from the notes by Richard Cleve and also the paper which I mentioned in the previous lecture, which was by Cleve and Mittal, ICALP 2014 paper. Okay, thanks, bye.